right, class, welcome to section 1.2, where we'll dive right in to talk about derivatives. So we'll be using the idea of a derivative for, well, the first 4 chapters of this book. So, as you see, it says slope of tangent line, we're going to talk about, okay, instantaneous rate of change, and then derivative. The good news is that they actually represent one and the same thing. So if we want to find the slope of a tangent line, we're going to find the derivative of that function. If we want to find the instantaneous rate of change, that means to find the derivative of that function. What is a derivative of a function? The instantaneous rate of change in that function at a point, which is measured by the slope of the tangent line to that function at that point. Okay. All right, so I'm going to start with the first word in that title, review what a slope is. I'm sure you guys already know, but I'd still like to review it with you. So, to measure the slope of a line, all we have to do, here's a line for you, all we have to do is pick 2 points on that line, yes? And so what does the slope of a line measure? The slope of a line measure how far up does this line go versus how far to the right. So the slope is simply a number that measures the steepness of a line. All right, and how do we measure that steepness? Well, you all know that we label the slope by the letter M. And the way we measure that steepness is simply the change, I'm going to just say this, the rise, right? So as I said, how far up versus how far to the right did we have to go. So rise over run. So it took me this far to get to the second point, and I went up by this much, yes? So the rise is nothing but the change in y coordinates versus the change in x coordinates. In other words, the vertical change versus the change in x coordinates. In other words, the horizontal change. Yeah, well, horizontal, it's there. Okay. All right. So how do we measure this? Well, super easy. The change in y coordinates, you simply subtract what y you got to minus what y you started with, yes, versus what x you got to minus what x you started with. So sure enough, you already have learned this, I'm telling you nothing new. Okay, let's move on. And first topic, before we get to the tangent line, what's a tangent line? Let's talk about a secant line. Well, a secant line is simply a line that crosses a graph through 2 points. Okay, so 2 points. All right. It could actually cross through more than 2 points. It's not a big deal, but we're looking simply at this. So I'm going to draw a graph for you. So let's say I have some kind of a function, and it goes up, and it goes down, and it goes up. It might go down again. It really doesn't matter. But this is what I'm looking at. I'm looking at picking 2 points on this graph and drawing a line. Okay. So as I said, it will definitely cross again down here. It crosses again, but what I'm looking at is 2 points. Yes. So The reason why we're looking at secant lines is because what we want to do is we want to measure the change in the graph of a function, the change in its y value. So let's say I might want to measure the change in the profit of my company. So I want to look at, hey, I'm about year 2 into my company, and then I'm about at year 5 into my company, right? So I want to know how did the change, how did my profit change in these 3 years? Now, what matters is that it's over 3 years, yes? So this happened over a span of 3 years, yes? And that the profit has changed from here to here. So what we could do with the slope basically is figure out what's the profit or change in profit per year. Now, sure enough, as you see, a bunch has happened ever since, right? First, in fact, the profit had gone down and then it went back up. And so, though with this secant line, if we want to go from this point to this point and we just simply make it a linear, kind of blur out this, and we're like, well, we were here and then we got here, this is what happened on average between these years, we could approximate that with the slope of the secant line, right? Just by drawing that secant line. So let me start writing this. So I'm going to say this: we can approximate the change, how about this, the average change, in a function, which again could be given by its graph, between 2 points with the slope of the secant line crossing through those 2 points. Okay, so this is what I'm again saying, that if you're looking at year 2, I'm making this amount of money. At year 5, I'm making this amount of money. And I want to figure out just an average. What happens between this and this year? One way to do so is to simply connect these points and simply measure the slope of the secant line, right? Now, would this be a good average or a good approximation? Not really, because again, as we said, first of all, we're seeing that the profit has gone down, then it's increasing up quite a bit faster, right? If I'm looking at this, kind of like blur it out and try and make it into a line, it's looking like it's going up way better now than if I'm looking at this average, right, at this secant line. But the point is, that's one way of measuring. Is it a good approximation? Not necessarily, right? Of course, if my function was going linear to begin with, right, and I want to see what happens from here to here, and I'm drawing this secant line, that's a good approximation. It's pretty much the same exact thing that happened, yes? And again, if your graph doesn't have to be a line, but maybe it's almost looking linear, then that's a good approximation. Now, if I want to figure out what happens between this and this year, and I'm figuring this out with a secant line, yes, so I'm connecting these points with a line, that's a secant line. Again, is this going to give me a picture of what happened in between? Not at all. We went up and down and up and down, but from here to here, it looks like there's no change, yes, even though there's quite a bit of changes in between, yes. So the idea, again, is that a secant line can approximate what a graph or what a function's been doing between two specific points, yes. Now, you want a better approximation? Well, take it slowly, right? Go from here to here, from here to here. So pretty much look at the big picture, yes. That's what a tangent line is about. Now, first of all, again, what is a tangent line? A tangent line is a line that just touches a graph in one point, at one point, I should say. There could be more later, but the point is, again, I'm looking at what happens specifically at a point in time, yes? So if I want, for example, to see what happens to my function at this point in time, yes, what I could do is I could just draw a tangent line, right? So this slope of this line is kind of giving me an idea. It's approximating this curve, yes? Yeah, it's going to touch later. Yes, it's going to cross later, but we're again looking at a specific point in time, yes? So here it is. Here's a graph, and here is a tangent line, yes? Okay. Now, what does this line do? This line, one more time, approximates what? The change, the actual change in the graph of this function at this point in time. So if you want to know what is an instantaneous rate of change in the graph of a function, where is a function heading at a specific point in time, right? Is it going to be changing? Is it increasing? Is it increasing faster? Is it increasing slower? Or maybe it's decreasing, right? We have a line that goes down, yes? What we do is we approximate that instantaneous rate of change in a function with the slope of the tangent line. So I'll write this down. So what we're interested in is finding the instantaneous rate of change in a function at one point. Great. So I can approximate the change in the graph of my function by that instantaneous rate of change in the graph of the function, right, at one point. So I can draw this tangent line, right? So at this point in time, this graph is heading just about this way. There is a problem, yes? So how do I find that rate of change? I find that by measuring the slope of that tangent line. And there's your first connection, yes? What do I mean? The instantaneous rate of a change in a function is measured by the slope of the tangent line to the graph at that one point, okay? So it looks to me like this graph is heading up, and it's heading up about this fast. Now, if I were to draw a different tangent line, let's say I would have this point right here, right? What happens to the graph at this specific point? It's still going up, but it looks to me like it's going up faster, right? At an increased rate. So yes, the graph is heading up, but it's heading up this slow, yes? Yes, the graph is heading up, and it's heading up much faster. You want another point? This one's going to be going up even faster and faster, right? So the slope of this tangent line is really telling us how fast the graph might be increasing. Where look at that, right? The graph is decreasing here if I'm drawing this tangent line. So it's going down now. So again, these are going to be important points. That's what we will be measuring. We want to know, right? Is there profit on the way up? Is it going up fast? Is it going up slow? Yes. What about the costs of our function, or the cost of our company? Are the costs of our company starting to decrease, right? Maybe they're starting to go up and they're going up faster, right? There's a problem. We need to look into it. Now, okay, so that's one thing. An instantaneous rate of change in a function is measured by the slope of the tangent line. Great. There is a problem with that. What is the problem? To find the slope of a line, what do you need? In order to find the slope of a line, you need what? 2 points, yes? Great, we need 2 points. Secant line, we're looking what happens from here to here. That's an average, yes, we do need, but we are given 2 points. So what happens on average, yes, between these 2 points? So great, we connect the 2 points with the secant line, and then we find that slope, no problem, yes? So the average change, let me write it again here, again is going to be what? The slope of the secant line, right? So you are given 2 points, so an average between here and here, figure out how much did your y values go up or down, and how long did it take to do so, right? By subtracting the y's and then subtracting the x's. When you're looking at an instantaneous rate of change, you only have 1 point. You do not have a second point, so how could you find the slope when you only have 1 point? All right, no problem. So, since we only have 1 point available on a tangent line, we cannot find the slope of that tangent line. But we could approximate that. How can we approximate that? We can approximate that with a secant line, and we can find the slope of a secant line that is close enough to that tangent line, okay? So I'm saying here it's the same idea that we used for limits. What do I mean by that? What I mean is we couldn't quite figure out what was happening at one point in the graph, maybe there's a hole in the graph, so we don't have an idea of what happens exactly when x was -3, for example, yes? But what we could at least do is we could approximate that value with values right next to an x of -3. So if we don't know what happens at a number, we could at least tell what happens close to that number, okay? Does that make sense? Okay, so here's a tangent line, and by the way, here's the graph of the y equals to x squared function. So I'm graphing, the red one here is the quadratic function, and let's say we want to find the slope of the tangent line at the point of coordinates 2, 4. So x is 2, of course, 2 squared is 4, so that's why you have the point of coordinates 2, 4 on this graph. And here's your tangent line, and we want to find the slope of that tangent line, okay? Now, we can't, because with just 2, 4, that's not enough, yes? So what do? We pick a second point on this graph. So let's say from an x of 2 to an x of 3, yes? And then, of course, 3 squared is 9, which is why the y coordinate to this point is that. So here I drew the secant line that goes through these 2 points, okay? Now, can I find the slope of a line that goes between these 2 points? Sure enough, right? And there it is. So let's find the slope of the secant line from 2, 4 to 3, 9, yes, that secant line that we have up above. So, of course, how do I find slope? I'm going to subtract the y's, subtract the x's, so as you see, we get a 5, right, for an answer. Now, is this secant line here a good approximation to this tangent line? Ish. Yes, so again, same as with the limits that we learned last time. Should we look at what happens here? Yeah, well, it's close, but could we get closer? Sure enough, yes. So let's draw a new secant line. What would make the approximation better, right? So again, I need to find the slope of this tangent line. My problem is I only have 1 point, yes. So what do? I pick a second point on my graph, right? And this time I'm going to pick one that's closer. Instead of going all the way to 3, I'm going to go to 2.5. Okay, so what's going to be the slope of this line from 2, 4 to my next approximation is 2.5, and 2.5 squared is 6.25. So what's going to be the slope? Well, 6.25 minus 4, the change in y values, over 2.5 minus 2, that's the change in x values, and that's going to get me a 4.5, right? Slope of this new secant line. Now, should I just say, oh, that's good, that means it's about 4.5? Or could I make it the approximation even better? Of course, we know the answer is yes, right? So how much better can I get? I could pick another point here at, let's say, 2.1, yes? And draw this new secant line. I don't want to make it too crazy, but it's not going to look so well. They're almost all starting to blur into each other. So let's go from 2, 4, the point of coordinates 2, 4, to one that's even closer, right, with my secant line. And that would be 2.1, and 2.1 squared, again, I'm on this quadratic function. Yes, I'm on this quadratic function, y equals to x squared. So 2.1 squared is 4.41. Okay. So now let's see what's the slope of this line. So 4.41 minus 4 over 2.1 minus 2. So 0.41 divided by 0.1, which is a 4.1. Okay. All right, so you might be seeing that these values are getting closer and closer, right, to a specific number as what? As we picking this second point closer and closer to this original one of 2, 4. Okay, let's drive it even closer. So how much closer can I drive it? I can drive it to a 2.01, right? All I need is a second point on this graph, right? And draw a tangent, secant line through that. All I need is 2 points. So from my original one, don't go too far, right? Pick one that's super, super close to it, right? That's when the approximation would be best. And 2.01 squared is 4.0401. 4.0401. Change in y's minus change in x's. Again, I already put it in my calculator, but you're welcome to check up on me. So this difference is 4.01. Now, clearly enough, we see that what is happening to these values. These values, we picked a point pretty far, right? And the slope of this tangent line is 5. But if I were to drive these lines closer and closer to my original point, right, for a better approximation of this tangent line, I see that actually the slope of that tangent line is merging to what value? To the value 4, right? So I'm going to write this down. The slope values seem to be approaching the value 4. As we pick points closer and closer to this 2, 4. Okay, so we can say pretty safely that the slope of the tangent line to the graph at the point of coordinates 2, 4 is equal to 4. Now, of course, What could have made for a better approximation even is picking a point to the left of 2, 4. You don't have to go to the right, right? But sure enough, if you pick a 1.99 and then square that, right? And you find that slope of the tangent line, right? Between those values, again, I just kept picking numbers to the right of 2, yes? But of course, we could have gone to the left of 2. We could have picked a point where x is what, 1.9, yes? Square that, see what value that is, and find that slope. Back again from 2.4 to 1.9, whatever that is. The point is that you would have definitely got another value is very close to 4. Okay, all right. So, what is our conclusion for this first part of the section? That the best approximation for the tangent line, yes, would be if the second point we are choosing is as close as possible to the point of intersection between the tangent line and the graph of the function. In other words, we choose a second point that is at a distance, let's say random h, from the first point, and we let that h value get closer and closer to 0. Okay. So let me draw a picture for you to introduce this h. Okay, so again, one more time. Here's the graph of a function. And whatever it is. And what we want to do is we want to find the slope of the tangent line to this point of coordinates x. Okay, its y coordinate, sure enough, is going to be some random y, yes. But I want to draw the tangent line to the graph at this point. Because why do I want to do that? Because I want an idea of where my graph is heading at this point in time. In other words, what's the instantaneous rate of change in this graph at this point in time. So as you see, at this point in time, the graph seems to be increasing. It's heading up, yes, but how fast? That's a difference, right? Somewhere up here, even though it's heading up, but it would be heading up much faster, right? So again, this is my tangent line. And I want to approximate, or I want to figure out the slope of this tangent line. Well, all I have is this one initial point on the graph where I decided to draw this tangent line, yes? So what do I need? I need a second point. Now, as we just said, the best thing to do is to pick a point that's super close, yes? 0.01 close, 0.00001 close, right? So from whatever value this x is, just add a little bit more, right? So what we're deciding is we're going to do what? We pick a second point, yes, on this graph. How far away from the first one? I said this should be an h distance away. So in other words, the second point here I'm picking is an x plus h, yes? So this point, the second point I'm picking here, in order to draw my secant line, which as you see is quite close to my regular line, yes? All right. So this second point right here, I'm almost not having enough space, but it's a what? Its x coordinate is an x plus a little bit more. So let me go back here to these pictures, right? At first, what did we do? We picked a point that was what? 1 unit away, yes? Okay, so this h distance from the first to the second point was 1. Then we said what? I'm going to pick a point where the what? It's just a 0.5 unit away from my initial one. So this h distance was just from 2 to 2.5 was just a 0.5. Then we picked an even better one, yes, 2.1. So again, the distance h from 2 to 2.1 was just a 0.1 unit, yes. And then we said I can even make it better if I make that distance from my initial point to my next one just a 0.01. And of course I could have gotten better with a 0.001. So this is what h is. H is the distance between my initial point and the second point I'm choosing, yes? So that's just an h distance, all right? So x plus 0.1 plus 0.01 is where my next x coordinate is. I don't know what the y of it is, but it's whatever I get if I plug in this x plus h into my function, whatever function it is we're looking at, okay? So here it is. And again, what will make the approximation best? If we do what? If we drive the distance, yes, between these 2 points as far as we, or as close as we can to 0, where we drive the second point as close as we can to our initial one, right? So there's my tangent line. This green one was my secant line. Okay? And what we want to do is we want to let this h be as close as possible to 0. So this distance between these 2 points we're choosing should be as good as nothing, okay? So, to recap, an average rate of change of a function on an interval from x to x plus h can be found by finding the slope of the secant line, yes, between these 2 points from my initial one, x and whatever f of x, y value I'm getting, and the second point that has coordinates x plus h and f of x plus h. Now the average rate of change from here to there is simply the change in the y coordinates minus the change in the x coordinates. Now, this is going to have some nice reducing as well once we plug in the values, but definitely x plus h minus x is just an h, right? So the distance, right, the distance between the x values is just an h, yes? Now, how do I find that slope of the secant line, or the instantaneous rate of change in a function, okay? So to find the instantaneous rate of change in a function, you find the slope of the tangent line to the graph, right? And how do we find that? By letting this average rate of change, right, get closer and closer to where h gets closer and closer to 0. So how do we find, going back to the page before, how did we find this slope of the tangent line? By merging these values closer and closer to each other, right? Making this distance between these points closer and closer to 0, right? So these values get closer and closer to 4. So that's what a limit is, right? So we are letting h get close to 0, so, and then we're approximating where we're looking at what do the y values get close to, right? What do these ratio values get close to? So that's the instantaneous rate of change, okay? So just to put it back together one more time, the instantaneous rate of change in a function is found by finding the slope of the tangent line to that function. And since this is just so important, is going to have its own name, and the name for that is the derivative of the function, okay, at this point x, okay? So to find the derivative, why do we find a derivative? To find an instantaneous rate of a change in a function, which is measured by the slope of the tangent line to that function. So that's the name of it all. So we don't have to, derivative is much less to say, okay? All right, now this is our notation. So we'll use this notation all the time. We call this f prime of x or the derivative of f of x, or f prime. So it's simply the derivative, the notation for the derivative of the function at the point x. Now there's a second notation for it. D over dx of f of x. So instead of putting the little prime on the function, we write d of dx, which is, again, it's standing in for what? The change in y's with respect to the change in x's of this function. Sometimes if we're using the y, you're going to see dy dx. Sorry. And that's how we read it, dy dx. dy over dx or whatever, but we just say dy dx and we know it's over, but yes. So either notation has its advantages, I should say. Many times if you say the derivative of a function, if you have it this, you have to have it defined up above. If f of x is blah blah blah, find f prime of x. This one, I don't need to define the function. I could just write it here, d of dx of 2x plus 3, right? So you know the function already is 2x plus 3, so you can write it in one notation. Both are being used anytimes. This one is Newton notation, and this one is Leibniz notation. Both of these, this obviously the famous English mathematician, this is a famous German mathematician. They both came up with the idea of a derivative at about the same time. There's no texting, no internet back then, even phones. So they each came up with this idea. They each gave it its notation. We mostly using the Newton notation, but as I said, the Leibniz notation has its own advantages as well. Okay, so we're going to continue in the next video.